We love new technology. We live to create it. We dare to challenge it so it becomes better and easier.
Turn the lights on and play my favorite playlist.
Think of your smart speaker at home. How many times did you come home and try to start your favorite music and it didn't work? Because your smart speaker didn't quite understand you? Here is a fun fact. It's not because of you. The key is the microphone and the voice processing. If you have a good microphone, you have a good conversation. Imagine you have a device that can hear everything.
Turn the lights on.
With the increasing numbers of voice-controlled devices, our needs and wishes towards technology raises too. They need to understand every command from within the room, but also if you are in the room next door. They need to work flawlessly, almost like an invisible assistant.
Lower the volume of the music.
With Infineon Premium MEMS microphones, you can finally have a device which never will miss any of your commands. It is time to be heard.
Turn the lights off.
Even from the room next door.
Mr. Mina Kim receives a bachelor degree in the electrical and computer engineering in 2015 from the Ulsan National Institute of Science and Technology UNIS, Ulsan, South Korea, and she is going to receive the PhD degree in electronic engineering in 2021 from UNIS. Her main research interests includes DC-DC resonant converter, wireless power transfer technologies, and power hardware in the loop simulation. Ms. Kim is a member of IGP Power Electronic Society and the Korean Institute of the Power Electronic Piece. Today, her presentation is a mitigation of the EMI from power converter using spread spectrum techniques. So let's go with Ms. Mina Kim. Are you ready? Mina Kim, are you there?
Can you hear me?
Yes, I can hear you. Okay, can you start share the screen? Okay, I see your screen.
Thank you for the introduction. Hello, my name is Mina Kim from Ulsan National Institute of Science and Technology in Korea. I'd like to talk about the spread spectrum for various power conversion systems. This is the outline. First, I'd like to talk about the spread spectrum for power converters and its advantages. And the second part will be about the theoretical analysis of EMI reduction performance of frequency modulations applied to the power converters. And the third and fourth part are about the previous research about the implementation of the SST for various power conversion systems. Lastly, I will wrap up the seminar. The electromagnetic interference, in short EMI, it is term of how much the electrical circuit induces the noise. Usually in power converters, high di over dt or dv over dt values are the major source of the EMI. So that's why the switch mode power supply the EMI is classified into two noises. First one is about the conductive noise. It travels along the physical routes between the equipment. And the radiative noise, in short RN, it radiates from the circuit to the air, so it may affect to the communication circuit. So in the chip level and system level, the EMI has to be avoided not to make the malfunction of the circuit. Conventionally, we have many EMI mitigation methods. First one is a proper layout to increase the noise immunity and low noise generation. As you can see in the right side figure, Usually we decouple the ground of signal level and power flow. It can increase the noise immunity of the circuit. And the second one is shielding. We usually shield the circuit for component level and the system level to increase the noise immunity. And the third one is about the soft switching. As I mentioned earlier, high di over dt or dv over dt are the major source of the EMI, but soft switching can reduce the the energy source of the EMI. So as you can see in the bottom side figure, you can estimate how much the soft switching can reduce the EMI generation. And the last one is about the passive EMI filters. It is most widely used in industrial field. It is powerful to reduce the EMI, but as you can see in the figure, it occupies large volume in the power converters. So it reduces the power density of the power converter and reduces the cost effectiveness. On the other hand, the spread spectrum technique, in short SST, it can reduce peak and quasi-peak values of the EMI without additional cost and volume. The SST changes the switching frequency or the other operating conditions. So it can spread the bandwidth of the noise. Assuming that the noise has constant total energy, by spreading the bandwidth of the noise, it can reduce the peak value effectively. And this slide is about how we can estimate the performance of this spread spectrum technique. As I mentioned earlier, the switching waveform is the one of noise source of the EMI. So assuming that switching waveform can be simplified with the sinusoidal waveform, the switching waveform without the SST can be expressed with a simple sinusoidal waveform, sinusoidal expression like this. But once we apply the SST to switching waveform, the theoretical expression can be changed the bottom side equation. The SST affects the switching waveform in terms of its center switching frequency and frequency deviation and modulating waveform. Here, delta F shows how much the switching frequency is changing, and modulating waveform shows how you change the switching waveform. So you can change the switching frequency periodically or randomly. But according to these equations, we can know that the total power of the switching waveform is fixed to a certain value. This shows the spectrum analysis results of the modulated waveforms. So according to the Carson's rule, the frequency modulated signals have bandwidth Fs twice of sum of delta F and Fm. Here Fm is the frequency of modulating waveform. So it denotes how much the switching frequency changes fastly. So as I mentioned, the total energy is fixed, but it can increase the bandwidth by frequency modulation. There is different spectrum characteristics for using periodic modulation and random modulation. For the periodic modulations, the spectrums and peak values are different according to the modulating waveforms. So you can see in the figure, the triangular waveform can reduce the peak value compared to the other modulating patterns. For the random waveform, the total energy is evenly distributed compared to the periodic modulation. So ideally, random modulation is the most powerful modulating waveform to reduce the peak value. This one is about the periodic modulation. As I mentioned, triangular waveform can reduce the peak value effectively, and it only has low computation burden. So much of previous work used the triangular waveform. According to delta F, the peak attenuation performance is different. the delta F, increasing delta F can increase the bandwidth of the signal. So peak attenuation is proportional to delta F. And the attenuation performance is dependent on FM value, but the FM determines the distance between the sidebands. So increasing, the peak attenuation is inversely proportional to FM. So the modulation index that shows the performance of the SST can be determined as this equation. The peak attenuation is proportional to modulation index M. So you can see in the bottom side figure, the peak attenuation performance of the periodic modulation is proportional to modulation index M. And this one shows the random modulation. Once you use random modulation, the EMI reduction performance of the random modulation is dependent on the randomness of the modulating waveform. So once you use random modulation with low randomness, you will have some pinnacles on your spectrum. And also the peak attenuation of the random modulation is proportional to delta F and inversely proportional to FM. So random modulation has the same modulation index, but what you have to see is that increasing FM increase the number of peaks, as you can see in the bottom side figure. So similar to the periodic modulation, increasing FM can reduce the peak attenuation performance. So the bottom side figure compares the peak attenuation performance of periodic and random modulations. Both of them can increase the peak attenuation by increasing modulation index, but ideally, random modulation has higher performance. And up to now, we observed the peak attenuation for first harmonic, but the switching operation of the SMPS has higher harmonic components. So, but the bandwidth of the higher harmonic is proportional to the order of harmonics. So once the order of harmonic becomes higher, then bandwidth increase. Bandwidth becomes larger. So at high order harmonic, there is overlap happens, but according to my experience, once the overlap is happened, the peak attenuation is very higher than before. So as you can see in the experimental result, the bandwidth of fifth harmonic is overlapped. So its noise has been disappeared as much as white noise. But you have to consider the practical implementation of the SST. The conductive noise is measured by voltage applied to LISN by input current of the power converter. So the theoretical analysis used the simple sinusoidal expression that simplifies the switching operation. But in fact, we measure the voltage applied to LISN. So the theoretical analysis cannot exactly estimate its performance. So as you can see in the bottom side figure, this shows the spectral measurement from the prototype. The purple line shows the spread spectrum technique with the largest modulation index. So purple line has to have the lowest value, but as you can see, the white noise affect to the spectrum. So the orange line has the lowest peak value, even though it has lower modulation index compared to the purple line. And there is second considerations. You have to consider the EMI standard. The CISPR 11 is one of the famous, popular EMI standard for power converters. The EMI standard, you have to check the EMI standard according to the application or characteristics of the power converter. But usually EMI standard restrict the resolution of bandwidth according to the measuring frequency range. But as you can see, the RBW affects the signal recognition. Once you use narrow band RBW, you can catch the signal perfectly, but once you use wide RBW, you cannot recognize the adjacent signals well. So that's why it can increase the EMI, decrease the EMI reduction performance of the SST. So this slide shows how the RBW affects to the spectrum. Both of periodic and random modulation, their performance is affected by RBW. And once you use lower RBW, it can increase the EMI reduction performance of the SST. For the periodic modulation, peak attenuation is possible even though RBW is higher than FM. However, for the random modulation, peak attenuation is impossible under high RBW values. So for a random modulation, it is required to have high FM value compared to the RBW. As I mentioned, the EMI standard has fixed RBW value. So I simulated the periodic and random modulations. For the periodic modulation, once you increase the FM value, it lowers the modulation index. So that induces the low peak attenuation performance of the periodic modulation. But once you use low FM value, RBW affects the spectrum a lot, so it induces also low peak attenuation. So when FM equals to RBW, periodic modulation can achieve the best peak attenuation performance, as you can see in the left side figures. But for the random modulation, as I mentioned, ideally it can spread the energy evenly over the bandwidth. So as FM becomes higher, it can obtain higher peak attenuation considering the RBW value. And this slide shows the periodic modulation example in previous research. The periodic modulation has three design factors: FC, FM, and delta F. FC has to be determined to provide desired power or voltage, so usually it is selected as nominal operating condition of the power converter. And FM, as I mentioned earlier, it has to be selected being similar to RBW to achieve high EMI reduction performance. But delta F, it has to be dependent on the power stage design, as the power stage design allows. And it also depends on the output voltage ripple. So this graph shows the boost converter's output voltage ripple according to the modulation index of the periodic modulation. Once the modulation index becomes higher, the delta F increases. So the output voltage has higher ripple according to the modulation index increases. So without any compensation method of the output voltage ripple, the delta F has to be limited. So that's why the periodic modulation's EMI reduction performance has to be limited. But with the output voltage ripple compensation methods, we can increase the delta F compared to the case of without compensation method. So we can increase the EMI mitigation performance of the periodic modulation. We have passive and active methods in previous researches, and this one shows the first passive method. This literature proposed the input parallel output series LLC resonant converter for spread spectrum technique. The converter has two different periodic modulation. So with this configuration, the output voltage ripple becomes higher. But with this modulation pattern, which has 180 phase shifted frequency modulating waveforms, the output voltage ripple is cancel each other. So the power converter, the total output voltage, it has very low output voltage ripple. And also the average value of the output voltage can be controlled by FC, which is the center frequency of the frequency modulation. So this slide shows the experimental results. Without the phase shift modulating waveform, it has high output voltage ripple here, but with the phase shifted frequency modulation, it has very low output voltage ripple. And also the LC resonant converters has very low conductive noise. And as I mentioned earlier, the output voltage can be controlled by center frequency. So this method can operate the spread spectrum technique under transient condition. And this is the second passive method. This literature proposed the half-bridge asymmetrical PWM resonant converter. And the resonant converter can provide us a flat voltage gain nearby the resonant frequency. So as you can see in this figure, lower Q factor provide us a flat voltage gain, and high inductor ratio can provide us the flat voltage gain. So although the switching frequency is changed as time going, but the output voltage ripple can be suppressed. And the inductor ratio has to be designed considering the soft switching capability. But in this literature, the output voltage ripple with the SST has very low output voltage ripple, even compared with the fixed switching frequency case. So the proposed method can operate the transient condition here. And also this literature has verified that SST can reduce the number of passive filters. This one compares the CN for different operating conditions. The red one shows the noise with the SST only using just one EMI filter, and the black line shows the CN without SST with second stage EMI filters. But the peak value of red and black lines are similar together. So that's why we can reduce the number of EMI filters. So the power converter can achieve high power density and high cost effectiveness with the spread spectrum technique. And this one shows the active method. This one proposed the LC resonant converter with hybrid controller. The hybrid controller has two operating modes, PSM and PFM. In steady state, it operates the PSM to reduce the output voltage ripple. In the transient state, it operates PFM to control the output voltage level. So as you can see in the mode selection logic here, the controller sends the output voltage, but the output voltage error is within the threshold. It operates the PSM. And once the output voltage error is higher than threshold, it operates PFM to control the output voltage level. This one shows the experimental results. The hybrid controller can effectively reduce the output voltage ripple, and also the CN noise by spread spectrum technique. But this active method cannot operate the spread spectrum in the transient condition here. So this one is a significant demerit of the active method. So to overcome this drawback, second active method has been proposed. This literature proposed the current-fed LC resonant converter to obtain the spread spectrum technique and output voltage ripple compensation method. The current-fed LC resonant converter has additional control variable by modulating the duty cycle of the inverter. So based on the characteristic of the current fed edge resonant converter, dual feedback controller has been proposed. This one shows the dual feedback controller. So the switching frequency changes by the spread spectrum technique as periodic manner, and the duty cycle changes its shape according to the switching frequency variation. So it has the same shape, and the average value of the duty cycle is changed by the output voltage level so that it can control the output voltage level according to the load condition. And the deviation of the duty cycle is determined by the output voltage ripple. So by sensing the output voltage ripple, we adjust the deviation of the duty cycle to minimize the ripple. This one shows the experimental results. You can see the output voltage ripple is dramatically reduced with the dual feedback controller. And also, this one can operate the spread spectrum technique under the transient condition. So we can know that the active method require additional control variable to operate the spread spectrum technique in transient condition. And this one shows the practical implementation example of random modulation in DC-AC converters. The induction heating appliances are representative DC-AC converters, but the IH appliances has to consider the pot because pot generates the audible sound according to the power fluctuation. But the periodic and random modulation induce the power fluctuation. So we have to analyze the power spectrum according to its modulating method. The output power of the IH appliances can be analyzed with this equation. But here, the voltage gain has time-varying parameter because as you can see in this figure, the SST changed the switching frequency. So we have to consider the changing voltage gain according to the modulated switching frequency. So this slide shows the power spectrum analysis result for periodic and random modulations. For the periodic modulation, it has power fluctuation like this. So the power spectrum has the frequency component in every nth harmonic of Fm. And its amplitude is proportional to delta F or output power. So if we increase the delta F to increase the EMI reduction performance, it induces audible noise. And also for the random modulation, I simulated the case with drastic switching frequency variation. Here, delta F step shows how much switching frequency is changed. So as the F step increasing, it increases the amplitude of the frequency components, and its amplitude is proportional to delta F. So once the switching frequency is dramatically changing, it induces the audible noise. So we have to suppress the amount of the switching frequency variation. Anyway, this slide concludes that periodic and random modulations, both of them can induce the audible sound from the pot. So in this context, I propose the random linear modulation that can eliminate the periodic waveform and the dramatic switching frequency variation. It interpolates the random reference linearly in period of TM. So its spectral analysis is similar to the case of periodic and random modulations. So ideal peak attenuation performance is, the random linear's ideal peak attenuation performance is middle of periodic and random modulations, but considering RBW, it has very similar characteristic to the random modulation. So it requires high FM value to increase its EMI reduction performance. But anyway, does not have periodic and drastic frequency change, it can eliminate audible sound theoretically. But in practical, the random linear modulation has discontinuous frequency change due to the practical digital signal processor. Digital signal processor changes the switching frequency after the switching is finished. So it has this continuous waveform like this. So we have to limit the delta F step of the random linear modulation not to make the audible sound. This diagram shows the maximum frequency deviation of the random linear modulation when the random reference is minimum and maximum. So delta F max can be calculated like this, and it has to be lower than delta F sound. And delta F sound shows the frequency deviation that induced audible noise. I measure the delta F sound as heuristic manner. So based on this equation, we can design the random linear modulation. As I mentioned, delta F has to be designed according to the nominal operating condition, FC, and soft switching condition. So I designed delta F based on the resonant network based on the voltage gain of the resonant network to provide the soft switching condition for entire operating condition. And also FM can be designed by this equation from this figure, not to induce the audible noise. So this shows the experimental results of the IH appliances with SST. The periodic modulation, it has a similar EMI reduction characteristic compared to the analysis results. When FM is equal to RBW, it can obtain the maximum EMI reduction performance, and the random and random linear modulations can achieve higher EMI reduction performance as FM increases. And this one shows the measured CN. As I mentioned earlier, the periodic modulation can reduce the amplitude of frequency component by reducing delta F. So I added the experimental results of periodic modulation with low F, but it can eliminate the audible sound, but it has lower EMI mitigation performance compared to the others. But the random linear modulation, which is expressed with orange line, it has comparative EMI reduction performance compared to the periodic modulation, as well as it can eliminate the audible noise from the pod. So this one shows the spectral analysis of the audible sound measured by the IH prototype. This one shows the periodic modulation. The sound spectrum has many peaks separated by FM, so we can hear the sound from the pod. And the random modulation, the overall amplitude of the sound spectrum is higher than others, so we can hear very loud sound from the pod. On the other hand, random linear modulation can suppress the amplitude of the sound spectrum as much as fixed switching frequency has. So I couldn't hear any sound from the pod using the random linear modulation. This is the conclusion. The spread spectrum technique for power converters, it can reduce the peak value of the EMI without additional cost and volume. And the peak attenuation performance of the SST can be estimated by theoretical analysis. Ideally, random has higher EMI reduction performance compared to the periodic modulation, but considering the RBW, it has different characteristics. The periodic modulation requires FM equals to RBW to achieve highest EMI reduction performance, but random modulation requires higher FM to obtain high performance. So I suggest the design methodology of the spread spectrum as first, occupy the maximum delta F as power stage or output voltage ripple allow, and select the best FM according to the modulating waveforms. And we look into the practical examples of periodic and random modulation. The DC-DC converters usually use periodic modulation to develop the output voltage ripple compensation method. The passive method, the output voltage ripple can be suppressed by power stage configurations, but the active method with single control variable, it cannot perform the SST under the transient condition. But active method with additional control variable, it can perform the SST under the transient condition. And for the IH appliances, random linear modulation has been proposed. The random linear modulation can eliminate audible sound, and also it can obtain the competitive EMI reduction performance compared to the other modulating waveform. This is end of my presentation. Thank you for listening.
Okay, thank you, Mr. Mina Kim. So everyone, if you have a question, you can turn on the microphone, ask question directly, or chat to the chat box. Okay, I think the first question from the Dr. Nguyen.
Okay, so hello, Minaki. I have several questions.
Yes.
Yeah, can you help me to share your presentation again? So the first question is related to the LLC. In the slide, you talk about the ratio between LM and LR.
This one?
Yeah.
Yes.
Here, like you said, like you need the low Q factor to get the flat voltage gain. So when you change the frequency, and then like the voltage gain, the output voltage will not change too much. So in this case, like, is there any problem with your modulation if like we add another external inductor in to increase the voltage gain, like when we control the Y output voltage?
Okay. By reducing the quality factor, it can increase the linearity of the voltage gain nearby the resonant frequency, and by increasing the magnetizing inductance, we can obtain flat voltage gain according to the switching frequency variation. But as you can see in this power stage diagram, if we increase the magnetic inductance here, it can reduce the soft switching range. So you have to design the magnetic inductance as considering the soft switching condition. And also that you may worry about the output voltage controllability, but this one controls the output voltage by APWM, so it can control the output voltage without the concern of high magnetic inductance.
Okay. So I just mean like in case I want to control a very wide output voltage range, so I need to increase the quality factor like as high as possible to increase the voltage gain. So in this case, like the modulation will be affected or not?
At that case, frankly speaking, this one only can give you very limited input voltage variation. So I recommend to use the active method shown here, because the current fed structure can provide you the wide input voltage variation capability. So this one can be the proper candidate, I think.
Oh, okay. And another question is related to the passive method.
Yes.
Like when you do the series connection of the output.
Yes.
Yeah, in this case, like you do the series connection of the output. So in the when we do the layout or when we do the transformer structure like this, and we have some imbalance between the transformer, so it will cause some different loss of the transformer, and then the output voltage will be unbalanced. So how is affect to your modulation?
Yes, it is true that the power stage design has practical difference between the converters. It induces the voltage or current imbalance between the converters. So it requires the power balancing method to eliminate that kind of imbalance. But in this research, we did not consider this kind of practical difference between the converters, but I recommend to use the power balancing algorithm to implement this kind of circuit in practical condition.
Oh, okay. So I have to use another power balancing modulation?
Yes, I'm researching on the power balancing strategy, but conventionally the master-slave power balancing method is most widely used, and it can it can successfully control the power imbalance between this kind of configuration. In this kind of configuration.
Oh, okay, I got it. So I'm sorry, I still have more questions. The another question is related to the PSM and PFM.
Here?
Yeah, in this case, like you set up the limitation for the VR.
Yes.
Delta VR to switch between the PFM and PSM.
Yes.
So do you have any hysteresis or just like do the comparison, and then what happened at the transition between the PSM and PFM?
Do you ask me about the hysteresis that affect the stability of the controller?
Yeah, I mean like you have the delta V0 there. So at the transition between the PFM and PSM, do you have any like special modulation to like add the hysteresis there, or just do the comparison?
Okay, I see. The threshold has to be designed the output voltage ripple in the steady state. The threshold has to be larger than the output voltage ripple in the steady state. It is because the frequent mode change between the PSM type in discontinuous manner, it can induce the instability of the power converter. But I didn't test yet. But conventionally, we know that frequent mode changing can induce can affect to the stability. So we recommend not to use frequently load changing circumstances.
Oh, okay. And does the output capacitance affect too much in your modulation? Like
this one, it has just usual output output capacitor. But if you increase the output voltage, output capacitor, it can mitigate the output voltage ripple from this spread spectrum technique. But it does not require that high output capacitor, because actively it can minimize the output voltage ripple here.
Oh, okay. And yes, sorry, I still have one last question related to your induction heating. So I'd like to ask, like, is your modulation will be affected by the material of the pot?
Yes, I told you that delta F sound here, it can be obtained by heuristic manner, because delta F sound is affected by the output power or pot's material or the other operating condition. So the demerit of the random linear modulation is that we cannot estimate the F sound for various operating conditions. So you have to consider the operating circumstance and pot. Based on this kind of background information, you can design this random linear modulation.
Oh, so that means like you have to have like special part or like some specified part for that, and then you cannot just change like any part you want, or in the case you want to change the part you want, so you have to design the delta F again, everything again.
Yes, but for using circumstances of the IH appliances, up to now we only use the typical part for the IH appliances, and I tested several kind of pot, and I select the minimum delta F sound not to make the audible sound for various pots. So I solved that kind of problem like this.
Oh, okay. Okay, I got it. Thank you very much. I think for the pot, like Dr. Han will be more familiar with this. Yeah, thank you.
Okay, thank you. I have a questions. So I see you change the frequencies. I think it's a hot topic. And I see you apply for resonant converter. So could we can apply this method to the non-resonant converter like traditional boost or buck converter?
I think your question regarding on the non-isolated power converter. As you can see in this figure, previous researches applied SST to non-isolated power converter because the non-isolated power converter can achieve unsensitive output voltage to the switching frequency variation. So frankly speaking, applying SST to non-isolated power converter is easier than resonant converter. So that's why we focus on the resonant converter to apply the SST with reduced output voltage ripple.
Okay, thank you. I got this. So could you come to the page number 26? So you change the frequency. So did you consider about the inductor current ripple, for example, in the L1 and L2?
Yes. Oh, pardon? So, I couldn't understand.
I mean, when we change the switching frequencies.
Yes.
So the inductor current ripple, I think, will be changes.
Yes, sorry, I couldn't upload the inductor current waveform here, but I measured the inductor current waveform. Once we change the switching frequency due to the SST, the inductor current also fluctuating according to its waveform. But applying the dual feedback system, dual feedback controller, it can mitigate the output voltage ripple. But also, it can also reduce the current ripple applied to the input inductance because it can stabilize the power flows. So by this dual feedback controller, we can reduce the output voltage ripple and input current ripple as well.
Okay.
So, yeah, what I want to say is that only using SST can induce that kind of fluctuation. So that's why we have to develop additional ripple suppression algorithm for the power converter.
Okay, thank you. I got it. So the next question from the Mr. Tang from Siuntech. So please, Mr. Tang.
Hello, my name is Tang from Siuntech. Thank you for your presentation. And I have a question about this slide also about the RLC converters. I don't know, this is current fed RLC converter. As I know, the current fed is the target, the purpose of current fed is used for wide range, as you said also. But in this case, it seems the duty cycle is fixed at 0.5. So therefore, I just curious about how we can say this topology with the resonant operation can be applied for the wide voltage range.
This one, its application is for the PV application, to deal with the wide voltage range of the PV panel. So according to this waveform, the yellow one shows the switching frequency and the red one shows the duty cycle. The average value of the duty cycle can change according to the load variation. So like this, once the input voltage is changing, the duty cycle can deal with the wide input voltage range, but I didn't put the wide input voltage experimental results in this slide.
Yeah, I see. You mean in this case, you not only change the frequency, but also change the duty cycle, right?
Yes.
So what is range of the duty cycle in your?
Well, if you use large delta F, it means that the output voltage fluctuation without the active compensation is higher, becomes higher. So it requires the duty cycle variation widely, but it can affect the soft switching range. So you have to consider the soft switching range, the duty cycle variation range that can provide the soft switching and the delta F simultaneously. So if you can, yes.
Okay, could you give me some exact number, like from 0.4 to 0.6 or example?
In this work, I used the duty cycle from 0.4 to 0.6 to cover, yes, the wide input voltage range and the output voltage compensation.
Yes, okay, thank you.
Okay, the next question from the Mr. Ding from the Hanoi University. Okay, please, Mr. Ding.
Thank you very much for your nice presentation. This is Dean from Hanoi University of Science and Technology. I have a couple of questions. Firstly, you have some spectrum measurement. So first question is, how do you measure the spectrum of the noise? Like use some carry-on instrument or like use chamber to measure, and what kind of standard you adopt to measure, to evaluate the spectrum?
This diagram shows the CM measuring equipment. Frankly speaking, we don't have any chamber, so that's why I couldn't measure the radiative noise. But for measuring the conductive noise, we follow this kind of measuring equipment. We put the LISN spectral analyzer and device under test on the insulator to decouple the white noise for the atmosphere noise, and we measure conductive noise from the power converter like this.
I see. So you measure only the CN noise, right? So
yes.
No radiation noise.
Yes.
I see. We are also conducting a project on fast charging station. We have to pass the CISPR 25 and CISPR 11, and we have to pass the band from 30 megahertz to 1 gigahertz, something like that. I don't know exactly, and it is very challenging. But I'm not sure about CN noise, but do you apply any decouple capacitors or only changing the modulation?
Decouple capacitor?
Input at the input side. Like you have the DUT, right? Device
yes.
and the testing. Then
yes.
you have two lines at the input side of the DUT. So do you apply any decouple capacitor there?
Decouple capacitor is not mandatory to measure the conductive noise. So we didn't put the kind of additional instrument to measure the conductive noise.
No, I meant it is not for measurement, but for attenuate the noise, because the decoupling capacitor like 104.
You
putting
mean
in parallel.
You mean Y cap or X cap, like that?
Like that, yes.
Yeah, we put that kind of capacitor to reduce the effect from the atmosphere. Yeah.
So your study is to combine both the capacitors and also modulation, or either of them, or both, or I'm not sure about like what kind of technique or the objective you trying to implement, because for example, in my case, sometimes I could not change my modulation. I just adopt some passive components to filter out the noise. Then in your case, so you use them both, active and passive, or only modulation changing, or how do you deal with that?
For the experimental results, I used the same measuring equipment, including the passive capacitor. So the performance enhancement has come from the frequency modulation and additional ripple compensation method. So I would like to say that this work has contribution to propose the frequency modulation with proper design methodology, and propose the random linear modulation, and propose the output voltage ripple compensation method in passive or active ways.
Okay, I see. One last question is okay?
Yes.
Okay. Regarding your answer to Dr. Nguyen Anh Dung about the design of LLC converter, I think next slide somewhere about AHB, something like that.
The LLC resonant converter for current
you show yes, this one.
Here?
Back. Oh, this one.
Yeah.
Previously, you said to Dr. Nguyễn Anh Dũng that you designed this converter for a very low Q factor for high magnetizing inductance, right?
Yes.
And for that, you can expand the substituting range of the converter. But in my experience, when I do so, my inductor ratio is about 10 or 11 something, because I need some kind of flat gain because my application is not charger, it is adapter. It must regulate the output voltage. But I suffer from one problem, which is when my input voltage change in a very large range, so I could not ensure or guarantee the self-switching. That is the first point. The second point is that because the switching range will be very large, then when I design the controller, I need to pick one point to design the controller. Then it is not a small signal anymore, because the frequency will change very largely, right?
Yes.
And the third point is when the frequency is higher, then the turn-off current becomes smaller, and I have to switch the MOSFET at very small turn-off current, and I may not get the zero voltage switching. So that is my experience. So do you suffer from the same problems when you do your experiment?
Let me summarize your question. The first one is about the magnetizing inductance design to provide the soft switching for entire load condition and spread spectrum technique. Is that right?
Yes.
And the second question was about what?
That is not a question. That is a point, not a question. Some point in my question. Yes.
You pointed about how to analyze its stability using the small signal analysis, because
like that.
And the third question, I couldn't hear your voice. Can you?
Already?
Yeah.
The last one is the switch off current. You always have ZVS, right?
Yeah.
But it must be done at some turn off current.
Yes.
Because the turn on current and turn off current of this a half cycle is the same but opposite sign, right?
Yes.
Then when your switching frequency is high and your magnetizing inductance is also large, then your turn-off current will be small. Then it may not suitable, how to say, the dead time. You change the dead time. If you do not change the dead time and your turn-off current smaller than the minimum turn-off current, then you lost soft switching, right? Okay. So that is the problem I suffer when I did my experiment. So I just want to ask if you do the same. You have the same things.
I think the first question and the third question are close each other, so I will answer you simultaneously.
Okay.
You pointed that high magnetizing inductance may affect to the soft switching condition. So in this journal paper, we also consider the soft switching range according to the switching frequency variation and the magnetizing inductance variation. So frankly speaking, the magnetizing inductance has to be lower than 10 or lower in practical manner. So that's why it can further reduce the output voltage ripple. And also that's why we cannot increase the delta F infinity. So if you want to implement this idea in your converter, you have to consider the delta F and the output voltage ripple and the switching, soft switching capability simultaneously. The three factors affect each other. And the second question is about the stability of the converter. I couldn't find the previous literature that talk about the small signal analysis of the power converter using the spread spectrum technique. But usually the output voltage ripple that affect the controller is its frequency is lower than the bandwidth, the crossover frequency of the controller. So still we believe that the output voltage ripple does not affect to the stability of the entire control loop. And also for the induction heating application, it usually operates with the open loop system. So that's why we don't have to consider about its closed loop stability for the induction heating application. But for now, we agree that the necessity of the small signal analysis to evaluate its stability using the spread spectrum is required. So we have planned to research about the stability of this converter using the spread spectrum technique.
Okay, and the last point about the turn-off current.
Yeah,
turn-on current.
For the experimenter, for developing the prototype, we selected the MOSFET with very low output capacitance. And also we consider the turn-off current during the power stage design. So that's why I mentioned that the quality factor or magnetizing inductance have to be limited. So we already considered the turn-off current of the converter for entire operating condition. And also we use very low output capacitance, the MOSFET with very low output capacitance. So that's why we could provide entire soft switching capability.
Okay, I see. Thank you very much. Very in detail answer. Thank you very much.
Thank you.
Okay, I think we are very interesting about the presentation of Mr. Kim, but due to the time limit. So if you have a question, please contact to the Mr. Kim by the emails. So now it's a time limit. So thank you to presenter tonight presentation.